Okay, let's talk for a minute about the conservation of momentum. Momentum, like energy and mass, has to be conserved, meaning that the momentum we have before a collision has to be the momentum we have after a collision. So essentially, we can just write it mathematically as initial momentum has to equal final momentum, right? But what's the fun in that? If we're just looking at one thing here, who cares if it ends or begins with the same amount? Yes, okay, it conserves it in that item. What becomes fun is when we can talk about collisions. Now, with collisions, you have inelastic and elastic collisions. And basically, it's real easy to remember. Either it's going to come together and stick together, meaning inelastic, not bouncy, right? Not elastic. Or it's going to bounce apart and go differently. So you'll still have your two masses just bouncing off of each other. Bouncy, elastic, right? So let's talk about elastic collisions first. With an elastic collision, you have to have at least two items for a collision. So we're going to say the momentum of the first one, the initial momentum of the first one, plus the initial momentum of the second one has to be equal to the final momentum of the first one plus the final momentum of the second one. And we can break that down even more by going ahead and breaking down our momentum formula into things that we can actually measure pretty well. So now you have the mass of 1 times the velocity of 1 initial plus the mass of 2 times the velocity initial of 2. It has to be equal to the mass of 1, velocity 1 final, plus velocity, her mass 2 times velocity 2 final. All right. Okay, so you can see that the momentum here was conserved in the ending. You can also see that it remains two separate items that have two different velocities. That means they don't weld together, they don't stick together, they don't hit each other. In fact, we need to understand that momentum is a vector. That's why we put our little arrow there, because each of these velocities has a different direction. Same as before, by convention, up and to the right would be positive, left and down would be negative, and you could even go back and break down into vector components. So we could do this in 2 dimensions. We're not today, but we can. Next up, we have inelastic collisions. And with inelastic collisions, there's no bounce back. So it's basically you have the momentum of 2 or more objects, and when they come together, they end up welding together or sticking together. So you end up with just one momentum of one object, and you can see that right here. It just now has the mass of both and only one velocity. And that's exactly how we would end up writing out it in the longer version. We would start with that mass 1, velocity 1, plus mass 2, velocity 2. Notice I don't have to do initial and final, and this is why. Because our final thing here is going to be the mass of both of them combined times one final velocity. And we do that because, like I said, these have stuck together. They didn't have that elastic bounce. They're not elastic. So they didn't bounce back. Instead, they stuck together. Like think of like two balls of clay hitting each other and just melding into one. So if you're thinking about elastic collisions up here, the game of pool where you shoot the cue ball and knock the little other pool balls from side to side, those are elastic collisions. Inelastic collisions, maybe think of like, maybe even a car wreck where the front bumper gets welded onto the back of the next car because of such high heats and attack, and so it becomes one object that's moving afterwards. What's also really cool about inelastic collisions is you can do this backwards. So that means that I can start with one object that's made of multiple parts, and I can have it blow up or separate, and you would end up with multiple parts. And so really, this is how you would do an explosion. Because you could say it started with no momentum, and then each part had to go in opposite canceling out pieces in order to get rid of all of that momentum. Okay? So let's look at an example of an elastic collision. So we need a before scenario and an after scenario, and we have to get a good bit of data in order for us to understand and calculate what we need here. But if we see beforehand, we had a 5 kilogram mass moving at 5 meters per second, and it ran into it's going to run into a 3 kilogram object that's moving 3 meters per second in the opposite direction. Notice the arrows right now just signify which direction it's moving, but we'll use negative and positive, so that'll be positive, that'll be negative a little later on. Afterwards, so after the collision, we see that the 5 kilogram object is now moving in the opposite direction at 3 meters per second, and we don't know what the velocity is of the 3 kilogram object. I would go ahead and speculate that it would need to be a positive velocity, but even that is kind of up in the air right now. We'll see what it comes out to mathematically. So here we write out our formula in our generic form. We solve it for the variable that is unknown, the V2F. We end up with this for our formula for what's left. Notice we had to move this one over, so we subtracted it. And then we place in all our values. Notice that anything going to the left, I made a negative velocity. This one's going to be a negative times a negative, so this entire thing's going to end up being positive. But this one's entirely negative. And we can go ahead and simplify this. That's going to be a positive 25. This is going to be a negative 9. And this actually ends up being a positive 15, right? And so when we go through all of that, we'll get that the final velocity has to be 10.33 repeating meters per second in the positive direction, because it was indeed positive. So if you notice, that's going a lot faster than either of these were going before. But this ends up being the same conservation of momentum. So that's where occasionally you can have two things rolling along and one hits the other and it seems to really jet it going further, like in pool, right? And that's because of the different masses or different velocities at which they hit each other. So just for fun, for our inelastic collision example, I went ahead and did the bomb scenario. Because if you notice, a bomb would be sitting here, that's roughly a 10-pound bomb, and it's not moving at all. It just sits there. But there's about to be a reaction inside, which causes our explosion, right? That explosion then causes definite movement. It breaks apart, and you have different sized chunks, and we're just saying it broke perfectly in not perfectly in half, but roughly in half. And the part on the right, the 3 kilogram part, is moving at 30 meters per second to the right, in the positive direction. And so we have to figure out how far it is moving behind, or the 2 kilogram part is to the other direction. Now, as I write this out, I'm just going to go ahead and set up this mass. This first mass is just 1 and 2 combined, because we have to deal with all of it. And it has an initial velocity. And then we have our 2 different parts. This is our generic version. We're going to have to solve this for velocity 1 final. When I do, I get this formula, right? However, remember that this is actually 0, which makes that entire statement 0, which means we can simplify this to simply negative mass 2 times velocity 2 final divided by mass 1. And then it's just plugging in our numbers. And we plug in our number values, we keep that negative, which makes all of that momentum negative, that 90 momentum now, kilogram meters per second, and then divide it by 2 kilograms, and we get that it has to go at negative 45 meters per second in the opposite direction. And that's how we do an inelastic collision. Now, it's important to remember that there are in-betweens. We are doing perfectly inelastic and perfectly elastic. If you look at a lot of things, it might have a tiny bounce and then kind of mold together, or it might have a really big bounce, but not as much of a bounce as it did before. So we're only looking at perfect inelastic and elastic collisions. Also, This is the base level to where you don't have to do a lot. You have to have a whole lot of information up front. We are going to learn that you can be a little bit more useful where you have two variables. But for that, we also have to consider energy, which is up next.